as having to calculate the load on something that might look like this. Right? The next one we'll do is probably more common, where we take a couple W shapes and we stick them together and we're going to load that, right? So this is a little trickier, a little simpler, but can be tricky too. So anyway, let's remember the formula and how we go about this. So what we want to know is where the geometric center of this thing is. And if this beam is like, looks like this, right? It's really long. So this is just the cross section. So this is like this part of it. That make sense? So when we're doing these, we're just looking at the cross section of the shape, but the load would be coming down kind of like this on the beam itself, right? So that load is coming against what we call the x-axis, this x-axis, but we just don't know where it is. And that's what this centroid thing's all about. Like, where is the geometric center of this shape, this cross-sectional area? That makes sense? It's like you slice the beam, that's what it looks like. You know, if it was a 4x6, you slice the beam, you know, it looks like that, a rectangle. Super simple. But this thing is some extruded part, and we're going to make a beam out of it. All right, just wanted to make sure, you know, like, why are we doing this? And we need this number, like, we have to be able to do it. Look at that. Clean slate. Anyone remember the formula? So remember that Y bar locates the x-axis. So that's the first confusing thing is, oh, Y bar locates the x-axis. X bar locates the y-axis. And again, most of the time we just need the x. If we just have one loading condition coming straight down, we need the x. If there was a side load, I don't know what that would be, but some kind of seismic load maybe, then we'd need to know the location of the y-axis. All right. So what we're trying to find is this x centroidal axis, and Y bar is how we do it. And the equation was Y bar equals sum of the AYs, and I wrote little a because that's going to be individual areas, because we're going to break this shape up into its very simple areas. Okay. Over the total area. Yep. And the Y's were to each individual area. Okay. So you take a complex shape, this is a complex shape, and you break it into its simple shapes. You can do those simple shapes then individually. That's why we're summing all the areas times their Y distances. Okay. So what shapes do you want to break it into? Rectangle. I was hoping you would say that. I made it simple. I'm going to number it. Number 1, number 2, and then number 3. The whole, and that's a whole, will be its own shape, right? So you take this complex shape and you break it up into simple ones that you can easily find the area for, and you can easily find the Y distance to it. That makes sense? All right. So area 1, that's the rectangle, and you ignore all the other shapes. Like ignoring the hole, ignoring the triangle, just looking at the rectangle. What's the Y distance up to the x-axis of the rectangle? Yep. So Y1 equals 3. Makes sense, right? Y2. You'd have to remember a triangle and where that centroid is. And it is in the cover of your book. It's a triangle right here. It's the triangle, and it's the height divided by 3 or this base divided by 3 from the 90 degrees. So it's a third of something, right? So in our case, this distance is what we want, y2, and it's going to be what? A third of 6. Yep. And then we need the y distance to the centroid of the hole. And I put center line here, meaning it's kind of halfway in the distance. So that's y3 equals 3. So that's usually the hard part, is picking out these y distances to each shape. Areas are pretty simple. So if I just go for the formula, y bar equals area 1, what's the area of 1? Yeah, 6 times 10, 60 inches squared, and times y1. Three inches, right? And again, you'll see the book sometimes does tabular form where it says, oh, y1 equals 3 inches, y2 equals 2 inches, y3 equals 3 inches, area 1 equals, just tabulate it out and then put it in the formula. So, however you want to do it, it's fine. This is 60 inches squared. What is area 2? Yep. Area 2 is 1/2 the base, and the base looks like it's what? 4 inches. Is that right? This is 10, and this whole thing is 14. Yeah, the whole thing is 14. Sorry about that. This is 2. Yeah, sorry. 14 is all the way out. So 1/2 of the base is 2, half of 4, 2 times the height is 6. So this is 12. And then area 3 is pi r squared, right? Pi, looks like the whole diameter is 2. So 1 squared, pi r squared. Looks like it's 3.14 inches squared. So if I did it tabular, you want to do that first, and then you can just fill in the equation. So we already got A1, Y1. A2 is 12. Y2 is 2 inches. And we're going to add those two together because area 1 is a solid, area 2 is a solid. So they get added. Area 3 is a hole. So it's going to get subtracted. So area 3 is 3.14 inches squared. And its y distance was 3 inches, and it gets subtracted. And then all of that is over the total area. So the tabular form is kind of nice because all the numbers are just there for you to fill in. That would be 60 inches squared plus 12 inches squared minus 3.14 inches squared. What are you thinking about, Ben? He's not telling me. I get 2.14 inches. Check me on that. Guest speaker, John Dryden. Are you gonna make it work? Good luck. Oh yeah, good luck with that. Anyone else get that number? Yeah. Get my number? Good. That means there's a high probability we got it correct. So the rectangle was at 3. The triangle is down closer to 2, and then the hole is back up at 3. So it does make sense that it's like in the 2.83 region. So you logically look at your answer and say, oh, that makes sense. Plus, there's more mass down low, right? Even though we've taken the little hole away, there's still a lot more mass low than high. So it's not going to go above 3. It's not going to move up. Shift it down. Good. So when we do bending stress, just going to emphasize this right now. Bending stress is MC over I. C deals with the location of this axis, right? C is the distance from the neutral axis. That's what you just found, this neutral axis, to the outermost fiber. Okay, so the distance Y bar is what? 2.83. Yeah, what is it this way? So this also would be like a Y prime number. $3.17. Which one's bigger? The top one. That's the one we would use. But we didn't know 3.17 until we found Y bar, right? The location of the centroid. So C, we want to use the largest distance from this neutral axis thing, from this XX axis to the outermost fiber. And it doesn't matter that there's, less fibers here, more fibers here. It just matters that it's the outermost fiber, right? If it's a circle that you're working with, then that is the distance to the outermost fiber. It's the radius. Make sense? So when we get to bending stress, we need C. The only way to get C, if it's a wonky, complicated shape, which I won't give you on an exam, but that's how you'd find it. You have to go through all of this first and then go into bending stress, right? Okay, cool.
60 inches squared, inches of plane.
Yep.
Is that the actual rectangle? First part?
Area 1, which one's area 1? That's the rectangle. What's area 2? Yep. Hole. Yep. Yep. And when you do it, they're not going to be numbered, or it's not going to be divided up for you. You got to divide it up and number them out and then go for it. Right? It's the same process. We would only be interested in the Y if we had a what's called biaxial loading from 2 directions, right? We're going to focus on single direction loading. We're not going to load it this way. And if you think about most of our structural pieces, like a floor beam has other floor beams, right? And we don't load those floor beams. We don't side load them. I mean, seismically, when the earth shakes, it gets loaded, and people with PhDs can figure that out. No, we don't need that stuff. Is that fair? All right. So we should do one that is a structural steel shape, a common shape, right? So let's do that. This is out of the book. If you have the book and you want to look at it, or you can just copy it down from me. These are 2 W shapes that have been put together. So if it was a single W shape, just a W shape, everything you need is in the book. You just look up the area, you look up the centroid, you can look up the C value, you can get everything you need from a structural shape. So if you're given a W shape or an L shape or a rectangle, all of that's in the book. You just look that up, right? It's only when somebody gets cute and puts two things together that we have to figure it out. And this actually happens quite a bit. Especially, I think I showed you guys this. I'm gonna do it really light, but like reinforcing the web with some steel plates. Like the next time you get next to one of those big trailers, don't crash, but glance over at the structural member and you'll see a bunch of these plates welded to the main structural member. Well, that's because in a region, there was a high stress level, right? When they did the design. So instead of beefing up the entire trailer, let's just beef up where that stress concentration is, right? So that's what those plates are doing, is just stiffening regions of the beam. That's also why your telephone poles are like this. That's exaggerated, I know, but they have wider bases than they do have tops. I mean, that's why we like trees and we use them for so long. They actually have wider bottoms than the top, right? So they have this natural taper to them. That's because all the stresses, all the bending stresses are down there near the base. So we want more material here. And there's hardly any bending stresses at the top because the top's not bending, right? It's just moving around. So same kind of thing. Same formula, right? So the formula to find, I'm going to get rid of my little plate. So where do you think so here's the x-axis of this W530. And here is an axis for the W840 here. I'll call it X2, X1. Where do you think the combined x-axis is? Is it higher than this or is it lower? Definitely higher. We've added a whole bunch of mass to the top, right? So the combined axis that we're looking for is this, and I'm going to make it an XX axis. That's the centroidal axis of this complex shape. Okay. So that means we want Y bar. So same thing, we have two shapes. You need to number them out or somehow keep track of them. I'm going to call this 1 and I'm going to call this 2. So then this becomes Y1 and this becomes Y2 because we pull everything from the same location, that bottom, right? I'm going to give you a little more time to draw it. We only have two shapes. We only need four things. A1, Y1, A2, Y2, right? That's what we need to run this equation. What would the third shape be? We have a W shape. That's this thing. And we have a W shape. That's this thing. That's actually a pretty good question. I thought you were going to say an I shape because a lot of people call these things I-beams. W stands for wide flange. Yeah. So the flanges are wider. So an I-beam looks like this. Right? And then a W shape would look like kind of the same structural piece, but just in a W shape form. Looks like this. It's just a lot wider flange. So these are called flanges. We need to get that terminology because the book uses it. These are called webs. This is a web. flange and web. And the 530/72, I believe that might be a metric call out. Maybe not. This 530 is huge. It's not a formula. We're just going to look it up. Yeah, it's definitely a metric call out. So here is our table in the back, right? W shapes, metric, SI, Systems International. And it's in millimeters. So notice that the call out W1000, that 1000 stands for this distance, the total height of the W shape. It's not exact, it's nominal. So just think of like, same as 2x4, it's not really 2x4, right? W1000 by 222, what is the D dimension? It's really 970, not quite 1,000. But when you call on the phone, you can say, hey, I need a W1000, right? And they know it's a W1000, and we all know it's really only 970 millimeters tall. All right. So the call out is just a call out. It gives you the table to look it up, but then you got to look at all the details to get exactly how tall something is or how thick the web is, right? So that would be this thickness of the web, TW. Here is the base of the flange, right? That dimension. Thickness of the flange is here. So we can get all this geometry if we need it. But we can also just get what? Area, here it is. And location of the XX axis is just going to be, because it's symmetrical, it's just going to be half a D, right? It's going to be half of 970 if it was this W1000. That makes sense? So that's nice. We don't have to like do any calculating, but we do have to read the darn table correctly. So area 1. That's this one, 530 by 72. What is it? 9,100 millimeters squared. And for exams or quizzes or anything, if you need these, I'll have these attached to the quiz. So you don't have to get your ebook out if you don't want or whatever. What would Y1 be? Y1 is going to be half the distance of the total height or the D dimension of the 530/72. So 530/72 D dimension is 523, so we're half of that. 61.5 millimeters. So tag those units because they'll become a problem. I get 261.5. Oh, sorry. What is area 2? $840 by $329. These things are huge. 42,100. And then Y2. Now it's on its side, so it's going to be what? This is tricky. Be careful because Y2 is, where is it? It's good to draw these things in. That centroid is right here. Oh man, it's so hard to do. Right? It's right there. So you need this distance and half of the web to get Y2. So Y2, and I'm going to actually write it out, It was the D dimension of our 530. That's 523. Going to be 523 plus thickness of the web of the 843.29. Thickness of the web is 19.7. Divide by 2 because I only need half of it. So tricky. Big drawings are good. They're going to help you. So what is that? 523. $532.85. Yeah. Now we have the parts and pieces to do the equation. Y bar equals A1 Y1 plus A2 Y2. All over the total area $483.58. Anyone else get that? Ray says no. Dang it. I might have screwed up. What do you get? Whoa.
Yeah.
Like I'm rounded. All right. 484. I must have missed a decimal there somewhere. Shifted it way up, right? Like here's halfway, 261. That's right here. How tall is this first piece? 523. Yeah, it's way up here. Right? Like to scale, it's like way up here. So that C value is definitely this value that we'd use in the bending stress. It's pretty big. Good. I like the formula. It's kind of fun. Like it's super easy to screw it up when, especially like that, finding the Y value of the location of that piece because it's laid on another piece and you have to do the thickness of the web and that kind of thing. can get really tricky. All right, excellent. I gave you 2 of them to do for homework. Let's take that away and look at the calendar. It is 22 and 25. Going to be good practice for me to like review these to make sure I've given you good ones. So that's, hey, come back, 22 and 25. That's this one, which is just like the one we did. So I think you're set. And then this one, which is pretty easy. You're just going to have to come up with some creative shapes. So like if you do a half circle, right? Maybe half circle, triangle, rectangle. That's how I have it broke up. Yeah, there is. Half circle is here, front cover of the book. So
We would have to do the whole circle and then after we get corrected out, we can cut that.
ooh, that would be trick. Half circle be the way to go. Just remember, your half circle is not in this position. Right? It's okay. So just be careful with that. But it's symmetrical this direction. It's not symmetrical this direction, right? So yeah, think it through. 22, 25. Good. All right. The what? 22, is that the C shape? Yeah. It's in the back. It is different. It's a C shape. But all of the information is back there. Danner, when you can have a home game where I can come and eat popcorn and heckle players and boo at the umpire. That didn't get rained out. It was probably during spring break or something. I could probably find the schedule online. You don't have to tell me. We'll see how persistent I am. But I'm going to give it extra credit in all my classes to come and heckle. Isn't there another student in engineering that's on the baseball team? You don't know of one? No? Okay. I've had several in the past. All right. Nice job. All right. Stick with it. Don't miss a homework assignment this term. Anyone not miss a homework assignment this term, I'm going to give you a big reward, like a pizza or something. I'm going to stop the recording, but it's just because I just thought of it. All right.